Hi, everyone. Frank here from TargetedTechTalk.com. Today's episode, we're going to be covering a very interesting project, global positioning system, satellite tracker. So normally you might use GPS to determine your location, but based on the signal that's out there for GPS, you can actually kind of turn the tables and get some additional information about all of the satellite signals that are reaching your location. So that's going to be the focus of today's episode. So this includes a full technical walkthrough for those that are more technically inclined that would like to reproduce this project on their own. I'll provide enough detail and the source code on my website so that folks can do that. If you're sort of not in that camp, looking to reproduce it yourself, we're going to cover a lot of interesting topics around GPS and the concepts, and we'll kind of see the hands-on demo. So it should be a good presentation for everyone. All right, so introduction here. So my goal with this project was to build a GPS satellite tracking device from scratch. So some of the benefits of this approach included understanding the solution at the component level and the protocol level. So really understanding, the information that was out there in the signal from GPS, understanding the GPS component, the antenna for the GPS circuit board, as well as writing the code to enable us to retrieve information from the GPS module. So really kind of end-to-end understanding a complete GPS system and building it from scratch. So GPS is used in many applications and platforms. It is pretty pervasive. It's used in drone flight control systems would be one example, and including both civilian and kind of small use drones as well as larger kind of drone systems that might be out there, or other vehicle systems. And then smartphones, a lot of smartphones do include a GPS chip or module at this point in time. And GPS is also incorporated into a lot of modern vehicles. So the objective with this project was basically a hands-on working lab. Kind of take these concepts from end to end and build the whole thing and be able to demo it, be able to talk about it in detail, and understand the complete concepts. So just not a theoretical kind of pictures and concepts kind of thing, more of an approach of getting the whole thing working, understanding the details, and then reproducing that in a lab and kind of reporting that out, giving a demo. So the full source code for the project is available on my website. So I'm not going to include that in the slides, but you can click the article link to get the full detail available later there. Okay, so from here, we'll stop this presentation. We'll show you a quick demo of the satellite tracker, and then we'll switch back to the rest of the slides. Okay, so that was a quick demonstration of the device in operation there. So there were a couple of abbreviations on the screen that I think I need to kind of sort of walk through in some detail, kind of explain what you're actually seeing. So that makes a bit more sense. So the top of the screen displayed the satellite count. I think that's pretty self-explanatory. There's a number of those satellites available, so the number is not fixed. It's actually picking up the information from the antenna that's associated with the GPS device. So there's some information that comes back from the GPS signal that's being transmitted, and we kind of walk through some of the detail here. So the first thing is what they call the PRN. The abbreviation is not that much more helpful, pseudo random noise, which basically, is just kind of fun engineering speak for not random. which means it's a unique identifier. So the PRN is the number that tells you what that GPS satellite is. The time is part of the signal, so that you can determine if that's a recent signal or if it's something older that somehow bounced back or something like that. The exact time is out there. The device that I built also displays the SNR, the signal to noise ratio. Basically, this tells us how strong the signal is. You can kind of see the different numbers go up and down for the different PRNs, so that identifies the signal strength for each of the satellites that's in range for the antenna. So, and sometimes it does kind of come back with some noise or some invalid data. You have to just kind of, scroll past those or kind of take that. So you can have invalid pings here and there, but for the most part, that signal to noise ratio is going to give you the signal strength. So for weak satellites, it's going to be like single digits. For very strong signals, it's going to be up into the hundreds. So might have a signal to noise ratio on the counter that I have, the scale we're using, up to 200, 300. Those are the strongest signals that might be direct line of sight, or the ones that are closer in orbit. The other ones, the signal drops out the further further the satellite is away, or if there's atmosphere or different things that are interfering with the signal, that would drop the SNR. But that's kind of a range. So building a device like this gives you a very good idea of what the strong signals are versus the weak signals and kind of the ones on the edge. So part of this GPS signal also includes the location info. So in technical terms, elevation and azimuth, or kind of go down to the protocol, longitude and latitude. So basically the location of that satellite that's out there. There's a number of frequencies that GPS uses, and here's a few of the most common ones. Depending on the age of satellites and the specific protocol that it's using, the 2 and 5 are the newer, and the 1 is the older protocol. So now I'll kind of go through some of the details of the parts list for this project. So this is kind of designed as a home lab kind of setup. So we've got a small breadboard, jumper cables are pretty cheap. And then this is the specific GPS module that I use. It's sort of marketed as a flight controller for drones, but it includes a ceramic antenna, but it's works just as well for kind of lab setup environments here. And it's fairly inexpensive. I think I got 2 of these units for something like $8 or $9. So fairly cheap. And then Arduino Uno, if you buy a new one retail, it's going to be about $25. And the 16 by 2 LCD screen. So if you followed along with my previous project, the only thing new would be the GPS antenna. The Uno and the LCD you can kind of reuse between projects. So that is our complete parts list. So we'll kind of go through the connections for anyone interested in kind of building this. And then this week I've got a complete wiring diagram to demo for the next slide. So these are the connections. So the GPS has a ground pin, a power pin. We're using the 5 volts for this one. This is really the only gotcha with the setup is with this particular model of GPS, it is kind of marketed or labeled as 5 volts, and it needs 5 volts or tolerates up to 5 volts for the input, but not all of the pins can tolerate a full 5 volts. So this RX pin, we put in a 1K resistor, so 1,000 ohms, just to kind of damp that down a little bit because that pin cannot handle the full 5. So that kind of puts it in a little bit of a voltage drop there, and then that pin handles it well and can kind of work normally. The other, and that, so just kind of from the GPS device, put in the resistor and then the connector out to the Arduino Uno D3. We'll see this on the wiring diagram in a second. And then the TX pin out to D4, and then I supplied the 5 volts and ground from the Arduino Uno. You're free to use whatever 5 volts and ground power source or you'd like. I just use the inbuilt one, but it just needs a 5 volt is assumed for this design. And then the LCD screen we saw in the previous project, ground and power, and then the 2 connectors, SDA and SCL to the Arduino A4 and A5 respectively. So if you're more technical, this is what the wiring diagram looks like. So I'll leave that up on the screen for a second. For those folks following along, I'll try to include a image of this as well in the article, so you can kind of have that up if you are building this. But fairly straightforward in terms of a project, fairly simple circuit. Really, the only gotcha is this 1K resistor that we need to put in place for the RX pin. Everything else kind of flows pretty straightforward there. So let's get back to some general GPS topics here. So I'll provide a link to this page, Wikipedia. So once you get that PRN number, which uniquely identifies a satellite, you can look up or grab some additional information about that particular satellite. So if you go to this page, that will match up the PRN number to that satellite. The only gotcha, I would say, in terms of analyzing that page would be it will list retired satellites. So when a satellite gets retired, they recycle the PRN number, so the unique ID goes to a new satellite. So if you look up your PRN and you see it's retired, just keep scrolling. There's going to be an active one further in the page. So this page includes details, the satellite group, or I think they typically call it constellation, the satellite name and details, the type of rocket it went up on, the site of the launch, the date of the launch. So you might get the official satellite name. That's not a number. You might get it, XYZ satellite or something. So this page basically has all of the PRN numbers out there that you might pick up with this kind of system. So if you're interested in the full details, that's kind of part 2. You can use those PRN numbers to look up the there you go. So observations and kind of learning from doing this experiment. So there is websites out there that you can use to look up GPS in. Some of those can be handy, especially if you don't have time to put together a project like this, or just kind of, this requires a little bit of electronics knowledge here. So those websites will give you a fairly good start. My observation is the websites are not 100% accurate. So there's a lot of satellites that are going to be on the edge of reception. So, I think when I did a couple trials here, I was getting, between 10 and 14 satellites that I was able to count and get get the PRN numbers from that I was receiving signal from. Those websites don't know your exact location. They don't know atmospheric conditions or other things that might impact reception. So typically with a device like this, the actual signal is going to pick up more than what is on the website, typically, or it might be a little bit different. So just kind of be aware, and that's kind of a learning here, is that those websites give you general info for what should be visible. It is not 100%. So if you're doing anything mission critical, you should not count on the accuracy of those general websites, because those just kind of give you ballparks based on what region you're in. the specifics about what signal you can pick up at your location, you really have to, look at an antenna kind of device. So some of the data is available on GPS devices where you might get some of this, a little bit of this satellite information. I don't think there's anything out there where you get this level of detail, being able to see all the raw information, the raw signal data, the level of detail. I think you get the most if you do put something together like this, but you can get some satellite information on different devices or different applications. So this is not a unique thing I put together, but it is, it's a good lab experiment to put together a complete GPS system. You learn quite a bit. So what else could we do with this? So there is an alternate design here. Really, if you have the LCD screen outputs can be optional. If you just want to connect this to a breadboard and your Arduino Uno, you could get the same information from the PC connect. So if you run this from the PC, you could get that without the need for an LCD. Get that information on the screen through what's called the serial output. The serial console shows up within the Arduino IDE Studio. You could get that information. So the LCD is not strictly required. Normally what you do with the Arduino is you create the program, attach it, and then you might have it up on the PC to upload the program and debug the program or get details. But when it's uploaded to the device, you can just plug it in no power source and it'll work. It doesn't need the PC. So that's one of the advantages of the Arduino microcontroller. But if you did want to go the PC connected route, you could just drop the LCD. That's not needed for the design, strictly speaking. What else could we do with this in the future to make this a little fancier? So what I demoed was the breadboard design. And within electronics, breadboards are very useful for coming up with prototypes, making sure you have good parts, good design, and it's good for stuff that kind of stays in place in kind of a home lab. There was kind of the one exception I did, the previous project, ESP32 Marauder. We used mini breadboards there. We were able to kind of use the adhesive backing to make that into more of a mobile device. Normally, like this kind of setup that I demoed, you wouldn't kind of move that around. But there's, with the GPS, there's, possibility the kind of upgraded design of this would be, if we look at a mobile version of this, what would that look like? That's pretty doable. So you might have a different specific microcontroller. So Arduino Nano is good, or ESP32 again, would be a microcontroller that's a bit better form factor. They're not as easy to prototype with, but they would be good for kind of that finished product, more compact. And those you do see more embedded in systems, especially the ESP32 is very, very popular as a embedded microcontroller in systems. You see that in TVs and all kinds of devices. So that's something to think about. We could have gone with a higher end LCD screen. So if we make this a mobile project, I displayed some of the GPS information. For me, it kind of worked out well to identify the unique satellite ID, the PRN, and the signal. Those were kind of the things I needed. And I was a little bit careful too about what information I shared, but the API would allow you to pull back the elevation and azimuth as well. So those could be additional fields if you're interested in that kind of detail. So if you had a little fancier LCD screen, that might be more of more of kind of the square screens, that not a step up from the 16:2 character screen that I had. A higher end LCD screen would be, kind of like a mini, a small TV or kind of a little digital device LCD screen where you could put text or graphics and stuff. So if you kind of went with a little fancier square LCD screen, a little bit like you saw with the ESP32 Marauder, that used an attached LCD screen. you could do something like that. And then that would enable you to put all that information on the screen. Honestly, I was part of the reason I just displayed some of the limited information is I did not want to, kind of dox my exact location. So I displayed what was most helpful for me, signal strength and the ID. That's going to give you some general info if you knew the time of day or whatever, but you wouldn't be able to track too much from it. So if you're just building it yourself, you might want additional detail. So if you want those additional fields that are available that I talked about, elevation, azimuth, you can add those in and get that on the LCD screen. So that would be an upgrade one could do. If it was looking to kind of a portable version of this, you would do this on a printed circuit board. I have an example of that on the next slide. So versus a breadboard where most of the components are kind of plugged in, the one bit of soldering I did for this project was the 4 header pins for the GPS chip. I did need to solder the 4 header pins on so that it worked with the board. It just kind of comes with the empty sockets, so you need header pins to work with a standard chip like this or a breadboard. So if you're just kind of doing the breadboard version, that's the only soldering involved, the 4 header pins. But if we go with a kind of a permanent solution or a mobile version of this, what would that look like? You would basically solder in all the components. So you would have fixed wires, and all the connectors would be soldered into a circuit board. We can take a look at an example on the next slide here. And then a rechargeable battery pack. So with this, you could have a small rechargeable battery, that it plugs in with some kind of USB connection. That is a lot of times that's on the microcontroller that you're using, and then you could take this out with a project box or a little junction box. Typically, you can buy little kind of plastic boxes, or if you get fancy, you can 3D print something to the exact specs and have a little plastic or even metal enclosure. For this one, probably want to use plastic so that you could get some satellite reception with the ceramic antenna that's part of the GPS, or feed it through the box and then mount the antenna on the outside. One of those two options. So, and the code that I use, there is general code libraries that allow you to put in some advanced features. So I did not write everything from scratch. I utilized a pre-built library and then kind of wrote my code on top of that, where you can put in some of these libraries, can actually take the information that we were talking about, the satellites, GPS information, put together multiple data points, and then track movements and speed of the satellites based on multiple points. So that's all possible within the libraries as well. So this is an example of a printed circuit board design. So I might be demoing this in some of the future episodes I do, but this is one where the components are soldered into the circuit board, the printed circuit board. So it's got a kind of a copper substrate with those little holes that you can see, and then you solder in the components to each of those, and both the front and the back side, you can kind of make the connections. This one is dual-sided that we're looking at. So you can make the wiring connections, and then this would be, kind of a permanent style project. So this would be something, if we look at taking what I did with the breadboard, if we want to upgrade that to a permanent solution and a mobile solution, we could use a printed circuit board, which is this kind of design. All right, so that is today's episode. So hopefully everyone learned a lot about global positioning systems and had a good demo of the end-to-end solution. And I shared a few of my learnings here about the putting together the system, and the full details will be on the article as well. So thanks for watching. See you next time.